In this section, we're going to look at some theorems about definite integrals. In general, we're going to try to understand a bunch of theorems that look at the bounds of integrals, looking at combining different integrals, using symmetry, and then talking about average value of a function. The main point of this section is to try to get more and more comfortable with dealing with definite integrals. The more comfortable you can be, the more fluent you are in the language of integrals, the better you can deal with the problem that you're unsure about. So we're going to try to become more and more fluent with some of the nuances of these things. So first, let's think about the bounds of the integral. These are the little numbers that tell us from what value to what value are we looking at the area for. So this theorem, let's let a, b, and c be any finite numbers, and f is a continuous function. Everything we're going to deal with in this section is going to require that we have a continuous function, as when you have discontinuous functions, weird things happen. So the first thing is just more of a definition than a theorem, and that is if you flip the bounds, instead of going from a to b, you go from b to a, then all you're going to do is take the negative of the integral. And that really is just a definition. There's really no mathematical reason other than we need to define what it means to have a bigger number on the bottom. Note that it is convention. It is, we say, normal maybe, to write the smaller number on the bottom and the bigger number on the top. So if you do have the bounds flipped and the bigger numbers on the bottom, it's already kind of a little bit weird, but there's going to be some spots where that might be useful, really just with dealing with some other theorems about these integrals. The next one is much more useful, and that is if you have the integral from a to c plus the integral from c to b, that's going to be the same thing as the integral from a to b. And this one I think we can understand with a picture. So down here, if we talk about the integral from a to c, that is looking at the area under the curve from a to c. And if we take that and we add to it the integral from c to b, that's the area there, then we get total the entire area from a to b. So it's like we've broken up this area into two separate pieces and we can add them together. And that can be a very useful thing to do in a lot of different contexts where we'll see some of them in this section, but also later on in chapter 6. So you can break up bounds into smaller chunks and then add them together because we're just adding areas together. Next, let's look what happens if we kind of change the function itself. So the bounds are going to stay the same now, but what happens if we add two functions or subtract two functions or multiply by a constant? And note that these rules that we have are going to be very similar to rules that we had for limits and derivatives. And the reason why is because derivatives are limits, and now we know that integrals are limits, right? A definite integral is defined to be the limit as n goes to infinity of a Riemann sum. So everything that happens with limits should also be true for integrals to some capacity, at least for these two rules. It's not really the same for multiplication, but it's the same for addition and constant multiplication. So here's our rules. F and G are continuous, C is a constant. If we take two functions and we add them together or subtract them, we can break them up into two separate integrals and add or subtract. And this is analogous to the idea that when you take the derivative of x squared plus sine, you don't have to think about that as one big function. You can do separately the derivative of x squared and the derivative of sine. We could do the same idea with integrals. A similar thing can be done with constants as well. We may have difficult constants to deal with in an integral, but we can just bring those constants out in front of the integral and we have an easier function to deal with. And this is going to be a very important thing to do, and it's the same thing that we had with derivatives, and we use that rule a lot so far. To give some reasoning as to why we can just add functions inside of the integral, past the idea of just the limit, we think about area under the curve, we think about these area of rectangles. So let's think about if we had the area of some rectangle, delta x is our base, and we have two different ones we're doing. We're having the f part here, so f of x sub I. The area of this rectangle is f of x sub I times delta x. And then g of x sub I is the big one here, and that's going to be, that's f of g plus x. So that means that, just the other rectangle here is going to be adding the function g of x. So we have this area is going to be g of x sub I times delta x. And you can take both of those, add them together, and get the area above, the area of the sum, f plus g. Another way to think about it, if you think about subtraction, if you had a bigger function g, smaller function f, and you wanted to look at g minus f, then you could think about the area from A to B, right? The area under the g curve minus the area under the f curve would give you this area, and this is the area of the integral of g minus f. So you could take the integral of g and the integral of f, subtract them, and you get the area in between. And in fact, that's really the same, that's going to be something that we look at in the first section of of Calculus 2, is looking at area between curves. And actually, it's the second section of Calculus 2, look at area between curves and doing things kind of like that. All said and done, this page, we can add integrals together, we can take a constant multiple, and we can break up a complicated function into smaller, manageable parts, as we've done with limits and derivatives before. So we talk about symmetry now. Symmetry, we're talking about if a function is even or odd. Remember that if f is an even function, we're saying it is symmetric over the y-axis. So that means that the function, I guess we have a picture of an even function right here. This is a picture of an even function because it is the same over that y-axis. An odd function is symmetric over the origin, which is another way of saying over the y-axis and then the x-axis. So this is a picture G of an odd function. So if we have these nice functions, some nice things happen with a specific definite integral. So if we look at the integral from negative a to a of f of x dx, that's the area under the curve from negative a to a, then that's going to be the same thing as just doing the integral from 0 to a and multiplying it by 2. Because we know that the area is going to be the same on the left and the right of the y-axis because it's a symmetric function. It's even, it's symmetric over the y-axis. So instead, we can just do 2 times the integral from 0 to a of f of x dx. And that might be a very useful thing because when we're doing the fundamental theorem of calculus, plugging in a and negative a may be time consuming. We can quicken it up by plugging in a nice value of 0. The next result is even more time saving. That's because if you have an odd function and negative a to a, then if you look at the two parts of it, if you look at from 0 to a, this is positive area, and it's the same magnitude as the integral from 0 to negative a, as that is negative area. So the positive and the negative parts are just going to cancel out, and we're left with just 0. And that's a very nice thing to do. It makes a whole integral immediate. What this is really saying is that the integral from 0 to a, there should be a g here, of g of x dx is equal to negative the integral from negative a to 0. Both those parts are the same magnitude but have different signs, so they cancel each other out and we're left with just 0. Finally, we're going to do one more result, and that is looking at the average value of a function. So again, if we have a continuous function, here we definitely need that a is less than b. We kind of assume that's the case for most problems, but we really need it here. The average value of f from a to b is going to be 1 over b minus a times the integral from a to b f of x dx. So let's talk about why this is true a little bit. So first we know that this is going to be the area under the curve, this integral. And then the 1 over b minus a is related to this, result right here, this value here, the length of that interval from a to b, that's b minus a. So if somehow we knew the average value of the function, then we could say that this area under the curve is the same as the area of the rectangle, right, where we have this average value. So we could say that the area is equal to this rectangle, which is going to be base b minus a times the height of the function, which is the average value. Then we take this and we solve for the average value, and we get our 1 over b minus a times the area, which is the integral. So this is a simple application of integrals. We can do some easy problems with that. But again, the entire point of this whole section is to become more and more fluent with integrals. When you're confronted with different bounds, different functions, can you break those up and make them easier? And this is the same kind of idea that, the first time you're dealing with lines, or you're dealing with functions in general, you're not fluent with them, so they're very difficult. But now you're much more fluent, so you can deal with a lot of different kind of problems. And that's the goal with doing with integrals and derivatives and limits as well. In the next video, we'll do some practice problems looking at each of these theorems and how to apply them to some kind of problems.